equal to 0 in a way, right? To find the critical points, right? And then test to see whether or not that critical point is a maximum or minimum, correct? By like just doing the second derivative test, I just plug in a number and you will see it. Here, the problem is that this function p right here is a basically it's a function of two variables. If you want to think about it, p and k, k and lambda, correct? So over here is in a way they fix lambda. They want you to find the value of k so that that guy is maximum, right? So well, theoretically you will take the derivative of that p with respect to k and set it equal to 0, find the critical point and things like that. The problem here is what? I don't know how to take the derivative of the factorial, correct? That's the problem. So, well, how am I going to do this? Well, just think about it for a minute. If you have a function, whenever you have a maximum over here, what got to happen right there? I mean, the slope is 0, but on the other hand, it also, I mean, like, we know that if we head that way, it's going to be hopeless because then we have to take the derivative because the slope is derivative, right? Set it equal to 0, and that's the problem. We don't know how to do that over here. So now the thing is that you should observe that like if this is a maximum, that means that the function is still rising over here, and on the other side it's falling. Correct? So therefore, if this is p of let me say k right here. Why don't I just call it k right here? Because I fixed lambda, so therefore it's just a function of k. So now, how about, okay, I want to find the point k right here, so that this one is a maximum, right? So let's say that at that k right there, maximum is a 10. So therefore, what does that mean? It means that your p of what? Of k is going to be, how is it compared to k minus 1? It's bigger than p of k minus 1, correct? Right? Because on the left hand side it's fallen. It's still rising, in other words, right? And then on the right hand side, you also have what? P of k is still bigger than p of k plus 1, correct? Right? Both of those got to be true. For the function p to attain maximum at k, right? So now look at this thing. Well, if this one is bigger than that, well, and pk is that, that means that what do you have? So look at the first one that he called it a right here, and this is b. Just look at a first. What does that mean? It means that you got to have lambda to the k over k factorial, right? To the e minus lambda got to be bigger than what? K minus 1. So it's lambda k minus 1 right here divided by k minus 1 factorial, right? E to the minus lambda. Agree with me on that? Yes? Okay. So here you can just have to say cancel the e lambda, e to minus lambda. Agree? Everything right here is positive, so therefore I can cross multiply over here, up here. So that means that I'm going to have what? K minus 1 factorial divided by k factorial is bigger than lambda to the k minus 1 over lambda to the k. Agree? So far so good? And that means what? K minus 1 factorial over k factorial, what is that? 1 over k. Correct? Is bigger than what? On the left hand side, on the right hand side, what do I have? 1 over lambda, agree? Right? And then b right here, what do you have? If you look at b, on the same thing right here, you have lambda to the k over k factorial, e to the minus lambda got to be bigger than p of k plus 1. P of k is that, so p of k plus 1 will be lambda to the k plus 1 over k plus 1 factorial, e to the minus lambda. Agree? So therefore I can just cancel those two guys right here, and I have what? Well, when I move k plus 1 on this side, just like we did previously, so I have this over k factorial is bigger than lambda to the k plus 1 over lambda to the k, correct? which gives you what? K plus 1 on the left hand side. On the right hand side you have bigger than lambda, correct? Right? So both of those right here got to be true. By the way, this thing right here is the same thing as saying that lambda is bigger than K, agree? Right? So both of those right here got to be true. That tells you that lambda right here is bigger than K and less than K plus 1. Right? And actually over here, the maximum right here, you can still have this one equal to this one if you want to, right? This might happen. So actually all those, the equality is allowed as well. So you have that. And that is the range for K and lambda. But now, however, in practice, I always think of lambda, the case when lambda is between 0 and 1. Why? It's just automatically. Why? Because right here, if you look at the Poisson distribution right there. E to the minus lambda. Right? If lambda is bigger than 1, things are going to decay extremely fast. Can you see that? Right? So in practice, you know, like all the models that you study, the fusion equation or heat equation or whatever, usually the case when lambda is between 0 and 1. Right? Because think about it, e to the minus 10. Even though over there you might have 10 to the k, which is a polynomial. But on the other hand, you have e to the minus 10, which is an exponential. Can you see that? So therefore, in practice, that is not really a good model. Usually, you know, like lambda is between 0 and 1. Is everybody clear of my point? I just want to make a point right there. When lambda is bigger than 1 in practice, the model right there is not really good unless you're studying some, you know, shock or something like that, shock wave, or, you know, like something that, you know, like boom, it's going to decay extremely fast right away. You see what I mean? Then that could be the model right there. But otherwise, if you want things to decay slowly, like you light a match right here and you study how the heat is going to be distributed and things like that, and it's going to be a slow process like that. Is that clear? So when I drop the solution to this thing and ship it to the trader, I assume that my lambda right here is between 0 and 1. Alright? So if my lambda is between 0 and 1, then in that case there is a quick way to do it. Okay, this one right here is when lambda is less than 1. Okay? If lambda is between 0 and 1, you can just form the ratio between P of k plus 1 and P of k right here. Right? And what do you get? Pk right here, remember the formula is this thing right here. Okay? So if you form the ratio between P of k plus 1 and Pk, you will have what? Lambda to the k plus 1 e to the minus lambda right here over k plus 1 factorial, and then you multiply by the reciprocal of that one, so I'm going to have k factorial right here, and lambda to the k, and this thing is e to the minus lambda, and you have this one cancel with this one, and this, and that leaves me lambda on the top and k plus 1 in the bottom. Right? Can you see that? Right? And remember, lambda is between 0 and 1. So that means that that ratio is strictly less than 1. Can you see that? Yep. Because lambda is less than 1, so therefore this one is less than 1 over k plus 1. And k is between 0, 1, 2, 3, and so on and so forth. Right? So therefore you can see that this one, the ratio is less than 1. So what does that tell you about a sequence pk? It's decreasing. Because the ratio of the next term over the previous term is always less than 1. Right? So that means that pk is a decreasing function. Correct? And what do you know about the decreasing function? Where does it attain the maximum? At the very first point, the original, the origin. Right? Okay? So here's the thing. A few of you pointed out correctly. In general, I work this problem out right here. My lambda is not given to me, right? It could be bigger than 1 as well. Then in that case, the correct range for k right here is going to depend on lambda, namely, where is it? Right here, lambda between k and k plus 1. All right. So if you give me a lambda, I will choose a k, 1 unit bigger than that. That's where it's going to attend the maximum. Is that clear? So now I'm going to instruct the grader. If you guys did it this way right here, right? Then I'm going to instruct how to give you full credit for it. All right? Because you are absolutely right. All right? Is everybody clear of my point right here? If my lambda is between 0 and 1, which in practice is the case, then you know you have a quick way to do it. Just form the ratio right there. You see that is decreasing function, right? But in general, if lambda is not between 0 and 1, then your k right there, it's going to depend on lambda. Can you see that? Right? Because, for example, right here, you cannot say that when lambda is bigger than 1, you cannot say that this ratio is strictly less than 1. Hence, the sequence is not increasing. Is that clear? All right. So either way, I'm going to instruct the grader to give you full credit if you do it this way. All right. All right. Now, any questions before I start?
Professor, this is Debbie from Salt Lake.
Okay.
I just have a question. I have my ratios the same thing as you have, but
Okay.
I end up with k being between lambda and lambda minus 1, just because the way I rearranged that, the ratios to be greater than 1 and less than 1.
Which one?
So instead of lambda in the middle.
So instead of having you have lambda
one right
between
here?
k plus 1 and k,
Uh-huh.
I have k is between lambda and lambda minus 1.
So it's rearranging.
Really? So what did you say? K is between what? K less than or equal to what?
So
Lambda?
less than or equal to lambda,
Less than or equal to?
and then and k is greater than or equal to
Oh,
lambda
over
minus 1,
here.
so on the other side.
Is lambda minus 1 here?
Yeah. Not the I dot.
That's a,
Did I do something right here wrong?
No,
Well,
they're
the
the
same
same
thing.
thing. It's
well,
just
I have the
rearranging
same
the
ratios.
variables.
That's why I can't seem to follow what I did wrong compared to you.
It's just a matter of putting it in terms of k or lambda.
Oh, probably you do right here. Probably what you did is pk and you compare it with the pk minus. Maybe what you did right here is you compare pk minus 1 and pk, which should be the
True.
same thing right here. Which should be the same thing.
That, the
It is the same
inequality is
thing.
the same. It's just
Yeah.
like if you were to subtract and put k in the middle, it's the same as your inequality. Just k's in the center instead of lambda.
So k right here is in the center and lambda.
Like if you those two up there when you set it equal, like using those two inequalities you have, like
So right now, if I subtract, let's see if I have this and this, they are the same. Let's say if I subtract 1 on both sides, what do I have? K minus 1 less than or equal to lambda minus 1 less than or equal to k, which is not this same thing.
No, but if you do it to the steps before.
So right here you have k minus, yeah, it's the same thing, exactly the same thing.
yeah.
You see? It's exactly the same thing. You and I, we got exactly the same thing. Look,
I got it. Now,
yeah, because if you subtract 1 on both sides, it's exactly the same, right? So it's like sandwiching. Can you see that?
yes, I can. Thank
Right,
you.
right, because
Okay,
if
I just want to make sure.
Yeah, if I subtract 1 from the inequality that I have, then I have k minus 1 is less than or equal to lambda minus 1 less than or equal to k. But then because k is less than or equal to lambda, that is the same thing as saying that lambda minus 1 is less than or equal to k less than or equal to lambda. Same thing. Absolutely.
We had a question on number 8, AII,
Okay.
on how to set up the parameters.
All right. So how about you hold on to that question? I'm going to continue with the lecture for a minute, and then I'm going to do the homework. Okay? Right?
That's fine. Thank you.
Okay. You're welcome. So now let's do this. Look at the continuous case. Now, if I give you a density function, because now we are looking at the Jones distribution. So f got to be a function of two variables, x and y, correct? Now, Sometimes some book even write it like this: f of x, y right here, and then x comma y, same thing. Okay, the notation right there is the same thing. So now, if it is to be a density function, then the double integral got to be 1, correct? So I got to have what? Double integral right here from negative infinity to infinity of f of x comma y right here, dx dy is 1. Right? Or, you know, like if you use some other weird looking region, not x and y, then, you know, like they just simply write it like this: double integral over the region A, and then let's say d capital A is 1. Right? Same thing, just like you learned from calculus. And now, if I have the density function like this, how do I compute the CDF? The cumulative distribution function is going to be a function capital F, right, of two variables. Let's say x, y right here, of little x, little y. How do I do it? Anybody? I integrate from negative infinity up to x, right? And then what else? Negative infinity up to y, of let's say f of uv right here, and then du dv. That's going to give me CDF, right? And now, if I have this thing like that, then you can see that by fundamental theorem of calculus, if I take the derivative of capital F right here, of both sides, with respect to x first and with respect to y later, in other words, I'm going to do it like this: partial square, partial x, partial y, of capital F of x, y right here. Then you know that by definition, what is that? It's going to give me f of x, y, correct? Huh? Take two derivatives right there. You're going to get back exactly the little f of x, y right there. And now, in the past, if you have a function of one variable, let's say one variable f of x right here, little f of x, how do you compute, which is the density function right here, how do you compute the probability of the variable x between a and b? You're just going to integrate from a to b of little function, density function, right? By definition, it's nothing but capital F of x minus capital F of a of b minus capital F of a, right? That's that. So now, back to our two variables problem. Now I have the density function f of xy. How do I compute the probability of, let's say, x right here between a and b, and then the variable y right here is between c and d? What do you think I'm going to do? Integrate f of x, y right here, correct? And let's say that if I do the x dy right here, x is between a and b, and y right here is between c and d, correct? Right? Or in general, if you just want to compute the probability of the how do you say joint variable x and y right here in some region A, right? Then what do? Notation y just means that I'm going to integrate f of x, y right here over that region A right here, and then say dA, right? From calculus. If I don't specify what A is, right? If we just use rectangular coordinates, then it's that. Otherwise, it's going to be that one right there. And now, I might as well brainstorm everything with you right now. If I have, remember in the case of discrete joint but discrete random variable, right? Think about it like you toss a coin 3 times and then denote x to be the event of the first head, and then y to be the number of the total number of heads, right? So then you can just talk about the frequency function of x and y. Think of it like that. And then now, in that case, beside the joint distribution function, or whatever you call it, joint frequency function, you also determine what else? The marginal whatever we call it, the marginal, what's the technical term for it? PDF, right? How did we define the marginal PDF? For example, let's look at the concrete case right here. Let me remind you of this thing right here, right? How did we define, let's say, the marginal of Y, right? When what is it? What's the technical term? The thing right here. Okay, right here. For example, if I want to calculate the probability of Y right here, let's say capital Y equal to 1. How did I do that one?
Y constant.
I'm going to keep looking at the case when Y equal to 1, and then I'm going to sum over X, correct? Remember that one? So therefore, what is it? It's going to be 2/8 right here plus 1/8, so you have 3/8 right here. That's the marginal Y when Y is 1, correct? And marginal Y when Y is 0, how do you do it? 1/8 plus 0 is 1/8 right here, correct? And then likewise, you can also calculate the marginal frequency function Px right here when x is equal to 0, for example. Then how do you do that? You're going to look at the row right here and then add everything up, you have a half, correct? That's the marginal. So in general, how do I compute the marginal thing? If I want to compute the marginal PDF for Y, right here, for example, for Y, when capital Y equal to something, right, I'm going to fix that thing and then I'm going to sum over X. Does that make sense? Right over here, in other words, is notation Y is going to be like this. The probability of P right here of what? Y equal to 1, correct? Because right here you keep it right here and then you sum over Xi. Sum over I. Sum over all the X right here, correct? And then if you want to calculate the marginal PDF for X, what do you do? Sum over P right here. Let's say that X right here is 0, you keep it that, and then you sum over Y. Is that clear? So whenever you want to find the marginal function of one variable, namely X, for example, you will sum over Y. And if you want to find the marginal of Y, you sum over X, so on and so forth. Now, exactly the same thing over here. We have the density function, John density function like that, f of xy. So therefore, if you want to find the CDF, the John CDF, that's what you did right there, right? And then you have exactly like that. Right? Now, you can also do the same thing like for the discrete case. Namely, you can do the marginal CDF with respect to only one variable. Is that clear? So, what do you think I'm going to do the marginal? Let's say marginal right here, CDF right here. So, for example, if it is f of x right here, what do you think I'm going to do?
Take the integral of a to b of f of x.
Okay. First of all, what does that mean? This thing right here, for example, it's going to be, let's say, x right here equal to some number, right? Correct? Some, let's say, a little x right here. What does that mean? Think about the discrete case, because this one is the continuous case. It's just like a limited case of the discrete one, right? So in the discrete case, if you want to find the marginal CDF for x, what did you do? I just explained. You keep x fixed and you sum over y. Correct? Sum over all the possibility for y. Likewise, exactly right here, if you want to find the marginal CDF for x, what do? You keep x right there and then you sum over y. And then sum over y means what? Integration. from negative infinity to infinity. That's the same thing, right? Remember, the integral sign, that is nothing but the summation when you take the limit, correct? So therefore, this thing right here, can you see that it's going to be the integral from negative infinity up to x right here, and an integral from negative infinity to infinity of f, let's say, of right here is, let's say, u. Maybe I should do it one step at a time right here, so that it's easy for you to see. This one right here means the probability of x, capital X, is less than or equal to x, right? That's by definition. Then this thing right here means you just have to take the limit when y goes to infinity of this thing. Right? We agree. Can you see that? Yeah? By definition, the capital F of x right here, the marginal CDF, it's nothing but you sum over all the y from negative infinity to infinity. That is the same thing as saying that you take the limit f of x, y right here and then send the variable y to infinity. Can you see that? Right? So therefore, what is this? What is this integral? Come on, guys. Negative infinity to x right here, correct? Yeah? Remember, there is a limit right here. Let me type step by step right here. And this is negative infinity to y of little f of, let's say, u right here. And then v, du dv. That's definition, one step at a time. Right? Correct? And now, when the limit right here, y goes to infinity, that is just like from infinity to infinity here. Correct? Yeah? So can I just write it like this? Minus infinity to infinity, minus infinity to x, and then minus infinity to infinity of f of what? Whatever, right here you have still u. Correct? Right? And the second variable that you integrate right now is going to be from negative infinity to infinity. Correct? So I might as well write it like u right here, and then this is du dy. Doesn't matter anymore. Right? I can just change the dummy variable. Look right here. You have y up here, so take the limit when y goes to infinity. This one is infinity, so it's that. And now you integrate f of uv du dv. So now, you know, like I'm going to fix u right here, because now I'm going to change v back to y and then du dy. Just dummy variable, right? Because I get rid of y already, now I can use it like that. Why, you might ask? Well, because now capital F of x is equal to this, right? If I take the derivative of both sides with respect to x, what do I get? On the left hand side is nothing but little f of x, right? And the right hand side is what? Integral and derivative, they kill each other. And leaves me with what? Negative infinity to infinity of f of what? Let's say x comma y right here, and then this one is dy. Yep, by fundamental theorem of calculus, I replace u by x in there. That's that. Alright? I see some blank faces, that worries me. Do you see the idea right here? Backtrack a little bit. You have little f of two variables, x and y right here. Right? You double integrate it. Like over here, you obtain capital F, which is cumulative distribution, John cumulative, right? And now if you want to find the marginal CDF, in other words, you just want to calculate capital F with respect to one variable x only, right? What does that mean? Notation-wise, it just means that you want to calculate the probability of the variable x to be less than or equal to x, right? And by definition, that probability is nothing but the limit of capital F of x, y when y goes to infinity. Because think of the discrete case. You fix x, you sum over y. That means you integrate from negative infinity to infinity for y. That is the same thing as this, right here. Okay? And now, think about that. F of xy by definition is this guy. So therefore, when I take the limit right here, that's the limit right there. Right? And now, that just means that if I pass into the limit y goes to infinity, so this one is from negative infinity to infinity, of f of uv du dv. Correct? But right now, I'm just going to replace it, the v by y back, right? Because it's just dummy variable. After get rid of y over there, I will have uv du dv right here. In other words, it could have been like this, minus infinity to x, and then minus infinity to infinity of f of uv du dv, right? But now I'm going to decide to change the dummy variable v right here to be y. That's all, right? I'm free to do that. So I have this, and now at the end of the day, I have f, capital F of x is equal to this thing. So therefore, now I can take derivative of both sides with respect to x. Left-hand side gives me this. Right-hand side, by fundamental theorem of calculus, the derivative will kill this integral, one integral right here with respect to x. So wherever I see u, I replace it by x. So this is x. Correct? So that's that. So at the end of the day, this is what I want you to remember. If I have little f of xy, which by the way sometimes people write it like this, then to find the CDF, it's going to be what? Integral from negative infinity to x, negative infinity to y of this thing right here. Or why don't I say u and v right here, so that it's not going to be awkward. U and v. This is capital U, capital V, for example. Right? And now, we just found out right here as well, if we want to calculate just the marginal CDF, then for f of capital X is going to be integral from negative infinity to infinity of f of x comma y dy. Right? Likewise, you can show that f of the marginal CDF for y is going to be integral from negative infinity to infinity of f of x y right here dx. That's the message right there to take home. Is that clear? Right? So if we want to find the marginal CDF for the variable x, you just have to integrate the Jones density function, but with the other variable dy. Just like the one that we did for discrete case, sum over y, if you want to find the thing with respect to x. Likewise, if you want to calculate the thing with respect to y, you sum over x. Is that clear? Right? Okay, good. So now with that in mind, let's do everything right now. I think there is one problem that I started yesterday but couldn't finish. Right here, back to this problem. I have f of xy, Jones density function to be c times x times y squared, where x is less than or equal to y, less than or equal to 1, and both of them are positive. And outside of that box, f of xy is going to be 0. Okay? And now I want you to find the constant of integration c to make this a Jones PDF. So how do I do it? Well, if this one right here to be a density function, then the integral over that region got to give me 1, right? Correct? So I got to have 1 equal to integral from negative infinity to the negative infinity of f xy dx dy right here is going to be 1. Right? And now how do I integrate this? Let's look at the region for a minute. What is the region that I am looking at? This is y, this is x. Right? This is, let's say x is 1 from 0 to 1, y from 0 to 1, so you have this thing right here. Yeah? And now the region right here is x is always less than or equal to y. Where is the line x equal to y? That's the straight line with slope 1 right there. And now x is always less than or equal to y. So do we look at the top half or the bottom half here? The top half. Right? So it means that this double integral right here, if it is outside this top half right here, it might as well be 0. Right? So now I have to integrate this. Now to integrate this, you know, like double integral, there is the easiest way to do it is this. Let's say that if I decide to do the y dx right here, it means that the outside limit right here got to be x, right? The inside limit got to be y. What are the limits for x? X go from where to where? X goes from 0 to 1, correct? As it should, because it's outside, so they got to be numbers, right? And then the inside right here, where is y? Y goes from where to where? No, y goes from x to 1, right? Because it never touched part down here, so it's going to be from x to 1, right? And then the function right there. Is that clear? And if I want to do, for example, the other way around, the x dy right here, and this one is the function fxy right here, and this is fxy. What is the limit right here? If I want to do this, then it means that the outer limit got to be y, correct? For y, and y goes from where to where? Y goes from 0 to 1. Can you see that? And then x go from where to where? X go from 0 right here up to y. 0 right here up to y, because it's never go beyond. Is everybody clear on that? Yes, no, maybe. Let's review quick right here from calculus. This is x, this is y. Let's say that I have some curves like that and then some curve like this. This curve over here is, let's say, some function. And then this is some other function right here. Right? Okay? And now, if you, for example, first thing first, if you look for x, maybe back to this one right here. So, dy dx, if you want to do dy dx, that means that the outermost right here is dx, correct? Right? So that means that where? This is the change in x. And what does that mean by the change in x? It means that I'm going to draw the straight line right here. Vertical lines, right? Because that's the change in x. That measure the change in x. Can you see that? Okay, always go by the outside right here. So this is the x, that means the change in x. So therefore I'm going to right here draw the straight line right here, right? From the beginning to the end of the curve, right? And then you can see that x right there goes from where to where? X goes from 0 to 1. Can you see that? Because that's how x varies. And now for y, how do I find the limit for y? You see, from the top, from the beginning to the end right here, the upper limit right here is 1 for y. And the lower limit for y right here is this curve, which is x equal to y. Can you see that? Right? Right here, if I draw this straight line right here, then the upper limit for y is 1. And the lower limit for y, see, right here, y, this is the measure in y, and this is the measure in x in this way. So therefore the upper for y is that, the lower for y is that. So therefore I have x to 1, 0 to 1. Y from x to 1 and then 0, x from 0 to 1. Is that clear? And if I want to do the x dy, how do I do that? This way right here, it means that I'm going to, but this picture is messy right now. Let me just draw another picture right here for you to see. Right? So we're going to look at the top half right here. Right? And over here, I want to do the outermost right here, which is dy. dy means the change in y. So that means that I now have to use what? The horizontal lines. Can you see that? Yeah? The horizontal lines. This is dy, so that means the measure, the change in y. So therefore the change in y means this one right here, this one, little line right here, right? And therefore, it means that for y, what is the limit for y? From 0 to 1. And the limit for x is going to be what? Remember right here, x is going to vary from here to always this line out here is going to be this line, correct? So x right here is going to 0 to this line right here. Right? And this line right here is x equal to y. That's why you have that. Is that clear? And for example, in general, if I have this picture right here, this one right here, let's say this one is some y equal to f of x right here, and then this is another curve right here, let's say y equal to g of x right here. Right? And now if you want to set up something so that, you know, like let's say that whole integral right here, dx dy, then how do I do that? Well, dy right here is the outermost right here. That means that I'm going to use what? The change in y, so it's going to be what? The horizontal lines. Can you see that? Right? So I'm going to test the horizontal line right here. Right? For y right there, what is the limit for y? Whatever this point right here is. Correct? Up to this point right here. Right? So therefore, let's say that this point right here, you can just find the intersection of the two curves. You will have the point right here, A, and this one is the point B, right? You can find the coordinate right here. Right? And now, for x, how do I do x? You see this thing right here, the lower limit for x is going to be this curve. The upper limit for x is going to be this curve. Right? Except that if this curve right here is y equal to f of x, so therefore I don't want to write this one right here, x right here is less bigger than or equal to fx, which is a little bit annoying, right? So I'm going to write it what? Y right here. Well, whatever the first curve right here is. Right? And this thing right here is the second curve right here. Can you see that? Right? And remember that, you know, whenever you do that, make sure that the lines right here, you got to touch one curve right here, and then on one side and the other curves on the other side, all the way from the beginning to the end. Otherwise, you have to split the limit. Right? So this is just a crash course in calculus. So now, with that in mind, back to our problem right here. Can you see that this one, I can set it up to be 0 to 1 and x to 1 of this one with respect to dy dx like that? Or another way you can do it is dx dy right here, then the limit is different. Right? So now you can just integrate this thing and equate that one to be 1, and you will be able to find c. Is that clear? Right? And now the next question is for this thing right here, part B. Find the marginal PDF of y. How do I do that? Look at what we just derived a minute ago. Right here. If you want to find the marginal CDF with respect to y, what do I do? I integrate the density function, the Jones density function with respect to x. Right? So what is that? What is that thing? Come on, guys.
CDF or PDF?
CDF, right? Marginal PDF of y. Yeah. So what is that?
So is it
The
the
same
two,
thing.
is it the two partials, like the little f of x, where you just go from?
That one is just like this, little f of y. Of y.
Oh, wow, yeah.
Okay? I guess when you say the marginal, they don't use marginal CDF. Marginal is marginal PDF. It's the same thing. Okay? So now how do I do this?
It's the,
Integral
it's
from
0
negative infinity to infinity of what?
f of x, y, dx.
F of x, y right here, and integrate with respect to the x. Can you see that? Alright. So now, what is this? Remember that x right here is always from 0 to 1. 0 to y, correct? It cannot be bigger than y, so therefore what is this? I might as well do this one from 0 to y. Clear? Of c, then x, y squared right here dx. Where c is whatever you just found from part A. Is that clear? Alright? So whatever it is, do it right here, you will get it. Integrate that thing, right? And now, how do I find the probability of x less than or equal to 1/2? And then what is this? And then y. Oh, this one right here doesn't make any sense. So this is x less than or equal to 1/2, and then y is less than or equal to 3/2. This thing right here is that. And y is less than or equal to 3/4. Okay? This thing right here, basically it's like the probability of x less than or equal to 1/2, and y right here is less than or equal to 3/4. Okay? How do I do that? By definition, this one is what? The integral over, what is that for x? From 0 to 1/2. Right? And then y is going to be what? 0 to 3/4, or can y go to 0? No, because your y right here is bounded below from x, right? So therefore this one is x, that's all, and this one is 3/4. And now the function is just going to be whatever that is that we just found for c right here, and this is x squared, and this is dy dx. You just integrate that thing. Is that clear? Yes.
Can you go back to part A?
Sure. Are we okay on that? Yeah? You can use either this one or that one to integrate to find c. Okay? Alright? And now to find the marginal PDF for y, you do this. Do it. Okay? By the way, if I ask you to find the marginal PDF for x, how do you do it? You integrate from negative infinity to infinity of the function right there, but with respect to y. And remember that y right here, the, how do you say it? The range for y is what? From x to 1. Because outside that it might as well be 0. Right? So that's that. And if you want to find the probability of x less than 1/2, y less than 3/4 right here, that means that you integrate for x, it goes from 0 to 1/2. And y right here, it goes from x to 3/4, because y is bounded below x. Right? So that's that. Very good. Okay, so this one is marginal PDF. Oh, okay. Sorry. Before right here, I think I used the wrong word right here. This one should be marginal PDF and not CDF. No wonder when you ask me that one. Right? Because this one is little f. Probability density function. It's not cumulative. That one is marginal PDF. And now, if I want to find the marginal PDF now, let's do it. How do I do it? This one is CDF. Okay, let's brainstorm it a little bit. How do I do this? I'm sorry? Yes.
Could you go over the difference between the CDF and PDF again? The
PDF
vocabulary
means
is
the
really
density
confused.
function. PDF means little f, little f. Okay? PDF means the density function, probability density function. Okay? And CDF means the cumulative cumulative what?
Distribution.
Distribution function. And that is usually denoted as capital F. Alright, so one is little f and one is capital F. Now, how do I find the capital F? actually, in a way, we already derived everything. I claim that it's exactly like this thing right here. This is marginal CDF or PDF right here. We already calculated the marginal CDF. Can you see that? It's exactly this thing right here. Before we take the derivative. Right? Remember, that's how we define the marginal CDF. It's like that. And then whenever you take the derivative of CDF, you get PDF. Right here. I claim that you already calculated the marginal CDF right there. It's nothing but this. Can you see that? Right here. That's the marginal CDF. You just integrate this thing right here from negative infinity to x, and then the other one is negative infinity to infinity with respect to y. Yeah? We actually derive everything all at once right there. Remember that, you know, whenever you are given a PDF, to get a CDF, you integrate it. Right? If you have a density function, you integrate it, you get the cumulative distribution function. And if you get a CDF, that means you get a cumulative distribution function. How do you get the density function? Take derivative. So therefore, it just means that right there. I claim that you already have everything right there. Right? Is that clear? Right here, this is my marginal CDF right here. Alright? Okay? So, like, let's put it right here so that you can see it. Capital F of x right here, by definition, is this. Right here, I'm going to put it back so that you can see it, how we derive it. What is this? This is this thing. So what is this? This is the limit, by definition, the limit when y goes to infinity of f of what? X and y. Right? That's that. And if you want to expand this out, is this the same thing as saying this? Integral from where? Negative infinity to x. And then what else? Negative infinity to y. Correct? And then what is this? This is what? F of, let's say, uv right here, and then du dv. Right? Just like what we did right here. Right? And now you take the limit in here, pass the limit to y, so that you have right here is minus infinity to x, and this thing is minus infinity to infinity, and this is f of u, and then v right here, and this is du dv. Right? And now, because there is no y anymore, that can confuse you right here, so I'm going to switch back the variable v right here to be y. That's all. So you have f right here of u, and let's say y right here, and this is du dy. Or dy du, if you wish. This one should be dy du or du dy. Dy du, right? Double integral right there. So this is du, yeah, du dy. And that's it. Right? And therefore, if you take the derivative of this, what do you have? On the left hand side, you have this thing. On the right hand side, what do you have? Integral from negative infinity to infinity of f of what? This thing right here, x, I have to replace u right here, right? Because when you take derivative, did I agree with you from fundamental theorem of calculus? If you have this one is from number a right here to x of f of t dt, this one, whatever it is, let's call it the function capital F of x. When I want to take the derivative with respect to x on both sides, the derivative of this thing on the right hand side, it gives me what? Whenever I see t, I replace it by x. Correct? So this is f of x. Yeah? And there is no more integral. Exactly right here. If I take the derivative of this thing with respect to x, that means that whenever I see u right here, I will replace it by x. Correct? And there is no more first integral, so I still have a second integral right there, and this is x comma y, and this is dy. Yep. Very good. So that's that. And likewise, so therefore this thing right here, we already derived everything. This is fxy right here, and the x. Right? Okay, good. So right now let's just do problem. Let me show you this problem right here, and then we do the homework problems all of them. Instead of pick and run problem randomly, why don't we just do the homework? All right. The Jones density function of x and y is given like that. Little f of xy is defined like that one for x between 0 and infinity, and y is between 0 and infinity as well. Now I want you to compute the probability of x bigger than 1 and y is less than 1. Okay? Don't look down here. Yep. Just how do I compute this one? Probability of x bigger than 1 and capital Y less than 1. What does that mean? Remember that whenever x is negative, it's going to be 0. So I might as well do from 0 to infinity, right? So therefore, if you want to calculate the probability of x bigger than 1, what does that mean? And y is less than 1. Let's draw a box right here. This is y and this is x. What is the probability of this thing? It means that for x I need to integrate from 1 to infinity, because x got to be bigger than 1. Right? That means that x, the whatever you call it, the limits for x will be from 1 to infinity. And what are the limits for y? Y is less than 1, so it's going to be from 0 to 1. Correct? Right here. So therefore you have integral right here for x right here it goes from 0 from 1 to infinity. And for y it goes from 0 to 1. Right? Because look, x is bigger than 1, that means that x right here goes from 1 to infinity. Right? And y right here is less than 1. Well, remember y cannot be negative, so the lower bound for y is that. So just put them in there, you have it. Just integrate that thing. It's easy to do. Right? I'm sorry? You have a question?
Is
You can
that-
press the button.
Oh.
Sorry? Just hold it and then take it out.
Is that x less greater than or equal to 1, or just greater than 1?
Ah, you know that for the integral, right? That point
We're just
doesn't matter.
approaching 1.
I'm sorry?
We're just approaching it. Or
It's the
formally?
same thing right here. If you want to put it right here, it's the same thing. Right? Because you already agree that maybe a couple of lectures ago, we already discussed that the probability of x right here between a and b right here is the same thing as the probability of a less than or equal to x less than or equal to b. Right? If you throw the n points in, it's not going to make any difference. Because the integral, the point right there is of measure 0. Alright? So now, how do I compute the probability of x less than or equal to y? Second part, same thing like that, but now I want to compute the probability of x less than y. Okay? How do I do it? Probability of x less than or equal to y. Well, just draw a box right here again, x and y right here, right? Correct? And now, what is the line x equal to y? It's this line, correct? And now, x got to be less than y. So am I looking at the lower half over here or the upper half up here? Upper half right here, right? So the region that I need to integrate over is this guy right here, right? So now you just have to decide whether or not you want to use the x dy or dy dx, right? So let's say that if I want to use the x dy, now you tell me, how do I do it? The setup right here. And then what happens if I want to use dy dx over here as well? Alright? So how do I do this thing? Let's say if I want to use dx dy, what are the limits? The outside right here is dy, correct? So what does that mean? If I look at this graph right here, I need to use the vertical or the horizontal lines. The change in y, what does that mean? The change in y right here, so I have to use the horizontal lines, correct? To go from top to bottom, right here. Right? Okay? Look at the horizontal lines right there. So for y, what are the limits for y? 0 to infinity. Correct? Because it goes up to infinity. Remember, my function is defined to be this. Right? Okay? So therefore, that's the limit for y. How about the limit for x? With respect to the x first and the y later. You will see that I will run into trouble. Why? Because the limit for y is always outside right here from negative x to x, correct? And then for x right here is from 0 to infinity, right? So when you integrate this thing, you evaluate from 0 to infinity, you have something of y, right? And then when you integrate with respect to y, and then the limit for y is negative x to x, then you don't have a number, you have something in terms of x, correct? So therefore, I'm going to choose this one. Is that clear? So therefore, over here, what is that? Negative x to
X.
of whatever the function right there is, you put it in. Right? And then what are the limit for x out here? And this one is dy dx. You just integrate that. Whatever it is, you will be able to find out what? C. Right? And now, what is the next one? Find the marginal density. What does that mean? Marginal density. This is marginal PDF, right? So whenever you want to call, you want to find f of capital X of x right here, what do? You integrate the density, but over y. So you have negative infinity to infinity of f of xy right here and then dy. Right? And remember that you are given the function f. Even though there's a c in it, but you know, when after part A you should be able to find the c. Integrate that thing, and remember that for y right here, actually y is going to lead only from negative x to x. And you see that? Right? So this thing right here actually is going to be just from negative x to x of the function c x minus x squared minus y squared e to the minus x dy. C you found from part A. That's it. And now the marginal density for f of y right here. Is there a question?
So if we're doing a marginal density with respect to y, we go from negative x to x, and if we do the marginal
No. The marginal density for y, you integrate over x. But the marginal density for x, you integrate over y. Right? Right here. If you have this one is...
I understand, but we were just curious about the negative x to x. Like
oh, that's because the limit for y, they told me that y right here goes from negative x to x. Outside that is 0. Right?
Okay, thank you, yes.
Okay.
Thank you.
Strictly speaking, it should be from negative infinity to infinity. Integrate that one with respect to y. Right? But because outside negative x and x, y is 0. So I asked, well, let's do it like that.
Can you put that last sheet back just for a second?
This one?
Yeah.
Right?
Now,
You have a question? Is everything okay now?
yeah, it's okay.
Right? Because right here, the density, if it is to be a density, it got to integrate to 1. So integrate from negative infinity, right? Either way I do is fine. But here I need to be careful right here whether or not I should integrate with respect to y first or x first, right? think about it for a minute. If I choose to do it this way, the x dy right here, then remember for x, which is the inner limit, it is from 0 to infinity, right? And then for y, this thing right here from negative x to x. So if I choose to do it this way right here, then my integral right there at the end of the day, it will give me a function of x, right? It won't give me a number. So I better use this thing right here. And now for this thing, y goes from negative x to x, but it's okay because it's the inner limit. And then for x, it goes from 0 to infinity. So when you integrate this thing, you should get a number. All right?
Should it be though? Should it be c on that last one? Should c be? Do you take c outside your integrations?
Yeah, because it's a constant, of course.
Yeah. Okay. Thanks.
You're welcome. If it's a constant, you can do whatever you want with it, right? Just tag along. And now for the marginal density for y right here is okay, right? You do exactly the same thing right here, negative infinity to infinity, but now you integrate with respect to x. And now for x, remember, it only leads from 0 to infinity, so therefore you have this function right here. That's that. And now the next question is find the conditional density. I haven't talked about that one, have I? Let's talk about that one right now. It's so easy when you see it. In the past, if you have two things, probability of, let's say, A given B, how do you find that one? It's the probability of
A and B.
A intersect B
Yeah.
divided by probability of B, correct?
Right above there, should that be dx? Was
Oh,
there
the x, of
a-
course, from here to here, this is the x.
Okay, thank you.
Okay. So this one is the conditional probability, right? So now, if you have a choice, what do you think I'm going to do? If I want to calculate the probability of x equal to something, let's say xi right here, y given that y is yi, right? Because I have two variables right now, right? Let's say that I want to calculate the probability of x equal to some number, xi right there, y given that y is yi. What is that thing? How do you think I'm going to define it? It's going to be exactly the same thing right here, namely what? Probability of x equal to xi and intersection, right? So right here, how about I say n, or just write comma, and then y equal to yi, correct? Divided by probability of y equal to yi. Can you see that? Yeah? Just the trivial generalization of it. So now, with that in mind, how do I find the conditional densities for the problem number 12 right here? Conditional probability, right? So what does that mean? It means that I want to calculate right here conditional density, probability density function, density. So that means that I want to calculate little f, right? Density f x given y right here, correct? Where you are given the capital X is equal to little x and capital Y equal to little y, right? Because this is the same thing as this. They are the same thing right there. This is density function. When you integrate this thing, you get that thing. But you know what I mean, they are the same in that sense. You just integrate this thing if you get the CDF, which is the probability right here. Right? Okay. So now, how do I find this thing? It's what? F of the common, the chance right here. Right? Divided by what? F of y. Yep. I wave my hand right there, but I think you should be able to follow, right? Because right here, hold on for a minute. From the past, you have probability of A given B is this thing. You are clear on this, right? And a minute ago, we decided that if you want to calculate the probability of John things right here, x equal to something, y given that y, the event y is equal to something, it's nothing but the the intersection of those two, right? Divided by the probability of the condition right here, right? Correct? But now, remember that the probability right here, by definition, is nothing but the CDF. Right? Correct? And the CDF right there is nothing but the derivative. The integral of the density. Right? So you see that there is also another relation for the density. Namely that if you want to calculate the probability, the density function of x given y right here, it's nothing but the John density over the density of y. Right? Yeah? You can just take the derivative, you get exactly that gap. Right? Yes, you have a question.
Well, so for like problem 12,
Right here, what is your fxy?
is this
6 over 7, the function that you are given, divided by f of y, whatever you just found out
So
in
the marginal
part.
density.
Yeah,
Okay.
just right here. Right here. Right? And if you want to compute f of y given x, how do you do it? What do you think it's going to be? F of the John right here divided by f of x. F of x you just found out right here. You just put it there. Right? Is that clear? Exactly the same thing. Yeah? For that matter, let's look at this. I may as well. You guys are good now. I mean, like, if you think about it.
Doctor?
Yes, go ahead.
When this is Debbie from Salt Lake.
Sure.
How do you know then independence or dependence there? Is that when the two of those would end up equaling each other?
Exactly. Remember that in the past, how did we define the event A and B are independent? They are independent if the probability of A intersect of A and B, which is A intersect B, is the same thing as what? Probability of A times probability of B. Correct? That's how we define the independent in the past. Right? So over here, if you have a John density function, how do I find that actually that John density function right there is independent? If you have f of xy is the same thing as f of x times f of y. Right? And for that matter, you can also look at the capital F if you want to as well. Right? You can also look at the CDF, which is capital F of xy. If that one factors, by that I mean equal to f of x, capital F of x times capital F of y, then they are linearly independent. Clear? Right? Come on, you guys should be able to figure this out right here. It's very straightforward. So therefore, if you have this one right here, they are independent. If this one is true, f y y, or capital F of x y, little x y right here equal to capital F of x x times capital F of y y. Either one, because they are the same thing. You just integrate them. You see that? Right? And then the conditional probability is exactly that, given there. So this is the conditional probability. Right? We will talk about that tomorrow. That's right.